Let's get started. So I'll start with some announcements. The chapter 19 homework is due on the 21st. The chapter 20 homework is due on the 28th. The chapter 15 quiz will be on Blackboard until the end of the day today. It's due today. The chapter 19 quiz. Name? Will be on Friday this week, the 21st. The chapter 20 quiz will be on Friday next week. Really? And there is a lab today. And the lab from last week is, of course, due today. So we're starting chapter 20 on atmospheric effects. We talked about the atmosphere sort of in general. Now we're going to go into some more specific things that happen, more specific weather effects. So we'll talk about the Bergeron process as it relates to the formation of precipitation. We'll look at different forms of precipitation, including rain, snow, hail, sleet, dew, and fog. We'll describe air masses based on their temperature and moisture content. We'll describe the distinction between warm and cold fronts. We'll describe the different kinds of lightning discharges and indicate which is the most dangerous. We'll talk over how to estimate the different distance to a thunderstorm using the equation distance equals velocity times time, where velocity is equal to 1/3 of a kilometer per second or 1/5 of a mile per second. We'll differentiate between an ice storm, a snowstorm, and a blizzard. We'll describe the basis of wind chill. We'll describe the formation of a tornado. We'll describe the formation of a hurricane. We'll discuss different types of air pollution. We'll differentiate between climate and weather. And we'll talk about the effects of carbon dioxide and methane pollution on climate. So the lower atmosphere, the troposphere, which we are in, is dynamic. This leads to frequent weather changes, as we've seen in the last week or so, because what the hell has been up with the weather the last week? And the movements and interactions of large air masses bring variation to our weather. So we've seen some dramatic movements of large air masses recently, especially with going from 80 to 30 something and snowing. So large air masses can move thousands of miles and can influence a region for a considerable time period. And the general movement of air masses depends primarily on the global circulation structure of the Earth. So we talked about the global circulation structure and how there are like predominantly westerly winds in the lower 48 states in the continental US. The contiguous, and that drives weather from west to east primarily. So one of the most interesting, one of the effects we care about when it comes to weather is precipitation. And precipitation is tied to condensation. Water vapor turns into liquid water. So in most situations, condensation occurs within an air mass when the dew point temperature is reached. Now, sometimes the water vapor can be cooled below the dew point temperature without condensation occurring. In this situation, the air mass is said to be supersaturated or supercooled. There are various things where you can do this. You can supersaturate solutions of like salts in water. You can supercool water, and then you can induce a transition very suddenly. So the thing is that water droplets don't form randomly. They have to build off of something. So they form around microscopic foreign particles called hygroscopic nuclei that are present in the air. And hygroscopic nuclei are things like dust, smoke, soot, salt, and various other airborne particles. And since droplets form around these nuclei, condensation provides a method that cleanses the atmosphere. So this is one of the ways that like particles of gunk gets removed from the atmosphere. And if the proper type and size of airborne particles aren't present, condensation may not occur, or it can be slowed down, it can be retarded. Now, when condensation does occur, it forms tiny droplets that are formed in updrafts, because it's formed when air cools down below the dew point. So that's usually occurring when air is rising. So when air is rising, the condensation forms these tiny droplets, and they're easily suspended as a cloud. So when you see clouds, those are made of tiny droplets of water. Clouds are liquid water. They're just lots of little droplets of it. For precipitation, or actual rainfall, you need to form larger droplets. And there's thought to be two main processes responsible for the formation of drops that are big enough to fall as rain or various types of precipitation. And those are coalescence and the Bergeron process. Coalescence primarily happens in lower, warmer clouds. The Bergeron process requires cold. Around here, in continental areas, the Bergeron process is the primary form of rainfall generation. And in fact, most rain is generated through this. So coalescence is the formation of larger drops by the collision of droplets. You have lots of little drops, they start to run into each other. They merge. These slightly bigger drops start to fall. As they fall, they sweep through the tiny droplets, combining with them, merging. Eventually, they get big enough that they split into smaller pieces by aerodynamic drag. And the process of coalescence is most efficient when the original droplets are large. So starting with larger droplets enhances the coalescence process because you don't need as many collisions to form the raindrops. So this coalescence primarily occurs in warmer clouds at lower altitudes with lots of water. Now, the Bergeron process, which is named after the Swedish meteorologist that proposed it, involves, this is thought to be the most important precipitation process. This is the primary form that precipitation forms. And the Bergeron process has to do with the fact that under the right conditions, you get a mixture of water droplets and ice crystals in clouds. And if the temperature is right, and this is actually true for most things, it turns out that ice crystals suck in water better than water droplets. So what ice crystals will suck in water vapor better than the water droplets, and basically what will happen is the water droplets will evaporate and the ice crystals will expand at the expense of the water droplets. There's a tiny difference in what it's called the vapor pressure of ice and liquid water. And the vapor pressure of ice is lower, so it's better at the vapor pressure of ice is such that it is better at consuming water vapor than the than liquid water. So what you need is you need ice crystals in the upper portion of the cloud. Arguably, you have supercooled vapor in the lower portion of the cloud, and mixing or agitation brings the ice crystals in contact with the supercooled vapor. What can actually happen is that you can have a mixture of ice crystals and water droplets, and the water vapor will evaporate off the water droplets and condense onto the ice crystals. So the ice crystals serve as condensation nuclei and grow larger from the vapor condensing on them. So here's a video about how the Bergeron process works. The vapor pressure of ice is lower than the vapor pressure of water. So the water vapor that comes off the water droplets gets sucked into the ice, basically.
Hi, class. I wanted to talk a little bit about...
That works.
Hi, class. I wanted to talk a little bit about the processes that form precipitation in clouds. And the two main processes that we're going to look at are the Bergeron process and the collision coalescence process. So let's start first with the Bergeron process. And the key here is that this process occurs in the higher, colder parts of clouds in the mid-latitudes over continents and over oceans as well. And so the key here is that they have to be cold, so it has to be clouds that are tall enough that you have a high part that's very cold. And in that cold part, there's the coexistence of water vapor, liquid water droplets, and ice crystals. So water is existing in all three phases, solid, liquid, and gas. And what's happening in the Bergeron process is that the ice crystals are growing faster than the droplets. So the key here is that precipitation is formed in the form of ice crystals. Now, when it finally reaches the ground, it can be rain because it may have melted by then. But the formation of the precipitation is in the form of ice. And there's a net movement of water vapor from droplets to ice crystals. So the reason that this happens is that the saturation vapor pressure relative to ice is lower than it is for water. So for example, if we're at a temperature of minus 20 degrees C, our saturation vapor pressure for ice is only 1, where it's about 1.2 for water. So if we take an air mass and we cool it, it's going to hit saturation next to the ice crystal sooner than it is going to hit it next to the water droplet. And so to illustrate the Bergeron process, we're going to look at two chambers. One that is filled with ice, so this light blue rectangle here is ice, and this dark blue rectangle here represents water. And these are two chambers that are separate, but they're both sealed. And they're both at saturation, so the little dots represent water molecules in the vapor form. And you can see that the vapor pressure over the water at saturation is much higher than it is over ice. And notice that it says the temperature is less than 0 degrees C. Now, water can actually be super cooled and still stay in its vapor form. And we'll talk a little bit more about how and why that happens. So what we're going to do now is open this barrier and see what happens to the water vapor above the ice and above the water. So we open the barrier, and what's going to happen is the water vapor molecules are going to move from where there's a high concentration to where there's a low concentration. So we have a net movement from high concentration to low concentration. We have a gradient, a concentration gradient here. And so we can see the water vapor molecules move over here. So now we're going to have a net movement into ice formation via the process of deposition. And so the ice crystals are going to get bigger. The droplets are going to get smaller. There's a net movement of water molecules out of the liquid water droplets. So essentially we're having evaporation of the droplets and deposition or growth of the ice crystals. So we've got a net water transport from the droplets to the ice crystals and an increase in the size of the ice crystals. So to illustrate the Bergeron process, we have this high vapor pressure around the droplets, and we have this net movement to the low vapor pressure region around the ice, and so the ice crystal grows and the water droplets shrink. So the key here is that the Bergeron process has to happen in really tall clouds. So notice where most of this cloud height, and what kind of cloud is this? It's got that anvil top. This is a cumulonimbus cloud, and it's over land. And so most of the cloud is at a height where the temperatures are below freezing. And so those droplets are getting pushed up by uplift in the cloud. We have the Bergeron process, which is causing the growth of the ice crystals that look like snowflakes here. And then as they fall, they pass this freezing point, they turn back to liquid, and it falls as rain. And this is how a lot of our precipitation here in Colorado is formed, even when it forms as rain, when we have these tall cumulonimbus thunderstorm clouds. And the same thing can happen over the ocean. You can see we have the formation of the ice crystals here and then falling down and passing the freezing point and then falling as liquid water. So the difference when we don't have those tall, cold cloud tops is that we have the water staying more as liquid. And this also happens in the regions of the tall clouds that are below the freezing level. So in the warm part of those clouds, the water still is liquid, and what happens is the tiny cloud droplets bump into each other and they coalesce into larger droplets. Now they get so big that they'll fall apart, they'll break apart as they fall, and 5 millimeters is the maximum size. So we start here with the cloud droplets colliding and coalescing into a big enough raindrop that can actually fall, and it might get too big, and because of friction and air resistance, it might break apart into smaller drops. And the coalescence occurs partly because of the electrostatic charge of the different water droplets. If we just relied on condensation growth, so this is droplet radius with time, if we just relied on condensation growth, those droplets wouldn't get big enough. And so we need that collision and coalescence process to make the droplets grow big enough that they can fall to the ground without evaporating before they hit the ground. So to compare what we have going on, this is our continental and some oceanic cold rain process where we have these tall clouds, really high vertical extent above the level at which the temperature is freezing. And so a lot of the formation is occurring as ice crystals. And if we have clouds that are lower down, where a lot of the cloud is below the level at which freezing temperatures occur, then we have the collision coalescence process becoming.
So the Bergeron process requires the mixing of like super cold water vapor or water droplets with ice crystals, and then there's a net movement of water from water droplets to ice crystals. The ice crystals get big, eventually they fall, and on the way down, when they pass through warmer air, they can melt and turn into raindrops. So most rain that you encounter started as little ice crystals and melted on the way down. Name? Kirsten? So modern rain-making techniques, you may have heard of cloud seeding or things like that, are based on the idea of the Bergeron process. The basic idea is that you use some technique to speed up the Bergeron process. So in one method, you use silver iodide crystals that are used to serve as nuclei for ice crystals, because silver iodide crystals have a structure very similar to that of ice. So it's very easy to build ice off of silver iodide crystals. So those serve as nuclei for ice crystals, which then grow and kick off the Bergeron process and form rain. Another method uses dry ice. And this is actually the first method that was used for cloud seeding or rain generation, where you dump dry ice pellets to rapidly cool a cloud, and you super cool the cloud, and that triggers the formation of ice crystals and speeds up the cycle of this transfer. So the dry ice changes from solid to gas. This rapidly cools the cloud, and this process, once the cloud is much colder, it's much more likely for larger ice crystals to form that will fall as rain. Now, Precipitation occurs in a number of forms. Things like rain, snow, sleet, hail, dew, or fog. The most common form of precipitation is, of course, rain. So you get snow if it's cold enough, basically. If the dew point is below 0 degrees Celsius, you get snow. Snowflakes are hexagonal, they're six-sided due to the hexagonal crystal pattern that ice forms in. Sleet falls directly from the cloud as ice pellets or forms when rain freezes before it hits the ground, as it falls through a cold near surface layer. So sleet is mainly it's rain that's been frozen on its way down, but it didn't form necessarily as crystals like snow did. And you can also have freezing rain, which is rain that is super cooled and freezes as soon as it hits the surface. And then hail are large pellets of ice. They form in these large thunderclouds with, they cycle up and down a number of times and build up in layers. So if you ever find a hailstone and cut it in half, it will have layers. So they form from successive vertical descents and ascents within the convection cells inside thunderstorms. And they build up. So you need a really big cloud that has a strong cycling convection cell in it to form hail. Now, dew forms when atmospheric water vapor condenses on various surfaces. So dew just forms from direct condensation of water vapor on a surface. You've probably seen this if you have like a cold drink, water condenses on the outside. Same process, just the land cools down or it gets cold at night, water vapor condenses out on various surfaces. So when the land cools quickly at night, water vapor will condense on available surfaces like grass or your windows, various things. And if the dew point is below freezing, that water will form directly into ice crystals called frost in a process called deposition. So frost and frozen dew are different and they look different. Frost has that spindly, dramatic looking ice structure, while frozen dew looks like frozen droplets of water. The general weather, so let's talk about air masses. So the thing is that your weather conditions, the general weather conditions you have at any given place depends largely on these vast air masses that move around the planet. And they move across the country. So an air mass is just a big body of air that takes on the physical characteristics, some physical characteristics that distinguish it from the surrounding air. And the main physical characteristics that distinguish an air mass are temperature and moisture content. So what generally happens is you have a bunch of air sitting over some location, and they're going to pick up the properties of that location. So if it's over the ocean, it'll get wet. If it's over the land, it'll be dry. If it's in a cold place, it'll be cold. If it's in a warm place, it'll be warm. And then those air masses get moved by various winds. And so when one of those air masses moves in, you get that air mass interacting with the surrounding air, but also that air mass is going to have properties tied to where it came from. So when a large mass of air spends some time over a particular region, it takes on the characteristics of the surface of the region. So the source region of an air mass is where that air mass got its characteristics from. And it will eventually move from wherever its source region is, and it will bring along its properties. You have a bunch of air that sat over one place for a while, ended up like that area, and then it moves somewhere else. So we classify air masses based on their source region. And it's fairly straightforward. There's one classification for whether it is over land or sea, which covers whether it's going to be humid or dry. and another classification that covers from what latitude it comes from. That represents temperature. So the surface air masses are either maritime, which is expressed with a lowercase m, or continental, which is expressed with a lowercase c. Maritime air masses are humid. Continental air masses are dry. And then temperature-wise, we base it based on the latitude they come from. These are Arctic, the coldest, then polar, the Arctic is a capital A, polar, capital P, still cold. Then we have tropical, which is warm, capital T, and equatorial, which is a capital E, that's the warmest. In general, in the US, you get maritime and continental, polar and tropical. You can get a little bit of Arctic. You don't really get any equatorial here in the US. And the global circulation patterns, they greatly influence the movement of air masses. And the conterminous US is located within the westerlies. So in general, air masses move from west to east. We happen to be in the middle of a giant flat area. So we get greatly influenced by whether air masses are moving up from the south or down from the north. Because there's nothing in the way to slow them down. So we get continental polar air masses from Canada that are cold, or maritime, cold and dry, or maritime tropical air masses from the Gulf of Mexico that are warm and wet. So here's a video about air masses. And the collision of those is what gives us tornadoes.
Air masses. An air mass is a volume of air that's defined by two things, its temperature and its water vapor content. Air masses can be huge. They may cover hundreds or even thousands of square miles, and they're going to take on the characteristics of the land or ocean that is beneath them. That is to say, an air mass that sits over the ocean will tend to be a humid air mass, while one forming over the land will be more dry. Now, there are 5 major types of air masses that impact the weather in the continental United States and North America as a whole. The first one we're going to look at comes down from far northern Canada, near the Arctic Circle. This is called a continental Arctic air mass, abbreviated lowercase c, uppercase a. The fact that it formed over land makes it a dry air mass, and because it is so far from the equator, up near the North Pole, it's an extremely cold air mass. Ca air masses rarely make it all the way down to the United States, though they do have an impact on our weather. The more common cold air mass that affects us in the United States is a CP, or continental polar air mass. This sort of air mass is dry and cold, though not quite as cold as an Arctic air mass. These swoop down from Canada and have a major impact on the weather in the northeastern United States. We also have wet, cold air masses that affect the northwest portion of the United States. These are called MP, or maritime polar air masses. The word maritime tells you it formed over the ocean, making it a humid air mass, and of course polar refers to it being cold. We may also see maritime polar air masses moving onshore from the North Atlantic Ocean. Let's take a look at some of the warmer air masses that affect the United States, starting with the continental tropical, or CT, air masses that move northeastern from Mexico. These air masses are very dry and very hot, and have a major impact on the climates of Texas and Oklahoma. We also have maritime tropical, humid, hot air masses that affect the United States. The major source of these air masses is the Gulf of Mexico and the South Atlantic Ocean. So these are a look at the major air masses affecting the United States. Remember, the abbreviations and names for these air masses can be found in your reference tables. And you should pay careful attention to the CP air masses, which move south from Canada, and the MT air masses that move north from the Gulf of Mexico, as those air masses interact in the eastern part of the country to create thunderstorms in the springtime and have a major impact on the climate for New York State. Thanks for listening.
So here are some of the air masses that interact with the US. We have continental tropical air masses coming up from Mexico, maritime tropical coming up from the Gulf of Mexico and the Southern Atlantic and Southern Pacific, maritime polar coming in from the Northern Pacific, continental polar coming down from Canada, continental Arctic coming down from Greenland and the most northern parts of Canada, and in theory, you could have maritime Arctic hitting Alaska, the northern parts. But down in the continental, in the lower 48 states, the maritime Arctic isn't going to really affect us. Now, when two air masses meet, the boundary between them is called a front. And when you have two air masses, one of them is going to be colder than the other. And so if the cold air mass is moving over a warmer surface, that's called a cold front. If a warm air mass is advancing over a colder surface, that's called a warm front. And then there are a few other weird exceptions, like when you have a cold air mass and a warm air mass running into each other, or things like that, but that's the general idea. So if cold air is moving over warmer air, the cold air is moving, the warmer air is staying roughly still or being advanced over. The warmer air is retreating. That's a cold front. If warm air is advancing over colder air, that's a warm front. So here is an animation and a video demonstrating the two types of fronts. So you can have, this is a cold front with a cold air mass moving into a steady, the warm air that was already there.
This animation is going to describe how precipitation happens at what are called cold fronts and warm fronts. These are weather systems that develop wherever masses of cold air collide with masses of warm air. And the name actually comes from war, where armies would meet along a battle line called a front. And one way to think about the difference between cold fronts and warm fronts is to think about which mass of air is going to win the battle. So we'll start with a cold front. This is a situation that happens where cold air moves in like a big wedge underneath warm air. Cold air is always heavier than warm air, and so it's denser, and it's going to tend to slide under the warm air and push the warm air upward. Anytime you have air rising upward, it's going to expand and cool and lose its ability to hold moisture, and this will give you a band of clouds and precipitation along a cold front. On weather maps, if you watch the weather on the news, you can see cold fronts marked by lines of blue teeth that point in the direction the cold air is moving. Along cold fronts, you typically have very intense local thunderstorms and rainstorms. So it might pour rain for a short time, but then quickly, usually within an hour or so, the front will have moved on. So a cold front is where the cold air pushes underneath the warm air, and you have high rainfall and usually intense thunderstorms. Now, the warm front has in common a couple of things with the cold front. One is that the warm air still goes up on top of the cold air, but in this case the warm air is actually pushing the cold air out of the picture. So the warm air is winning, and that's how you can remember it. It's a warm front. The warm air pushes against the cold air, squeezing it out, like imagine squeezing a watermelon seed between your fingers. It kind of squeezes out, right? And as the air pushes, it also rises up over the cold air. Rising air, again, loses its ability to hold moisture, and you tend to get clouds and rain. On long warm fronts, you typically have more mild, more mellow, more spread out rainstorms rather than really local intense thunderstorms. And if you're looking at the weather on the news, they mark warm fronts on maps with red half moons that point in the direction that the warm air is pushing the cold air. So that's cold fronts and warm fronts, major precipitation belts in many places on the Earth.
So because in a cold front, the cold air is moving while the warm air is sitting still, it ends up the border between cold air and warm air ends up much steeper, and you get much more rapid rise, and you tend to get more intense, more concentrated thunderstorms. When the warm air is moving over the cold air and squeezing it down, the slope is much more shallow between cold air and warm air, and you get more spread out precipitation. So cold fronts generally form a sharp, steep boundary. Where the lighter warm air gets displaced upward, you get more violent and sudden changes in weather. You get very intense, short storms, or relatively short storms. While warm fronts form a more gradual boundary because it's more difficult for the lighter warm air to displace the denser cold air. So the rise is spread out over a larger area. So a larger area gets rainfall, but it's not as intense, like it's not as concentrated. So you get lighter rain over a longer time. Now, weather maps use standard symbols to show different types of fronts. Cold fronts are generally blue triangles. Warm fronts are red half moons. An occluded front is when a cold front overtakes an active warm front. It's mixed moons and triangles. A stationary front is when a cold front and a warm front run into each other and sit still. That's, triangles on the cold in the direction the cold was moving, moons in the direction the warm was moving. These two are not very common at all. And the direction of the front's advance is indicated by the side of the line with the symbols. So this, all of these symbols here, those fronts will be moving up. So here's a typical weather map. Here we have a cold front moving this way, a warm front moving this way. Various, colors indicating temperatures, symbols indicating the type of precipitation, and the temperatures are listed at various locations. Again, another cold front here, another warm front there. And these are low pressure areas and high pressure areas. Now, what happens is you get these air masses moving across the country, you get areas of higher pressure and lower pressure. You get cyclonic low pressure and anticyclonic high pressure regions. Low pressure systems generally carry rising air currents, clouds, and possible precipitation. Lows are generally associated with poor weather, which is why if you look at a barometer like the one on the wall here, the low pressure region is labeled things like stormy, rain, things like that. While the high pressure regions are generally associated with falling air currents, clear skies, and fair weather. The falling air from high altitudes is very dry, so you don't get a lot of precipitation from that. While lows are associated with the warmer air near the surface that has a lot of humidity in it rising up from forming precipitation. So high pressure area systems carry falling air currents, clear skies, and fair weather. High pressure is generally associated with good weather. And the positions of highs and lows are monitored, and they're mapped using something called isobars, which are lines of constant pressure. So here are some high and low pressure systems in this video.
Hi everyone, I'm Marissa from the National Weather Service in El Paso, Texas. Today on Weather Basics, I want to talk about high and low pressure. Air pressure can tell us what kind of weather to expect. A sudden drop in air pressure usually brings stormy weather. We call this drop in pressure low pressure. Low pressure is usually represented by a red L on weather maps. At the surface, moist air comes together or converges then rises to create stormy weather. Surface winds in the northern hemisphere blow counterclockwise around a low pressure system. A good way to remember what kind of weather low pressure creates is to remember that low pressure generally creates lousy weather, like rain, snow, and wind. A rise in air pressure means we can expect good weather. We call this rise in air pressure high pressure. High pressure is usually represented by a blue H on weather maps. In the atmosphere, dry air sinks, then diverges or separates to create nice weather. Surface winds in the northern hemisphere blow clockwise around a high pressure system. A good way to remember what kind of weather high pressure systems creates is to remember that high pressure creates happy weather that is sunny, warm, and calm. So high pressure, happy weather. A way to further investigate high and low pressure is to build a homemade barometer like we've done here and track air pressure changes in your area. Here's our homemade barometer. All you need is a piece of paper, a straw, a balloon, some rubber bands, and a glass jar. As the weather changes, so will the height of the balloon, and the straw will rise and fall against the line on the card. If the air pressure rises, the balloon is pressed down and the end of the straw is pushed up. So if your straw is above the line on your card, then the air pressure is higher than on the day you made your barometer, and you will have fairer weather. If the pointer is lower than the mark you made on the card, then the air pressure is lower than on the day you made your barometer, and your weather will be worse. If you would like to make a homemade barometer like we did here, or for more information, head on over to the Weather Basics website linked below. Thank you for joining me today on Weather Basics, all about high and low pressure. See you next time.
And that design of a barometer, that basic idea of a sealed chamber that expands and contracts with the external pressure, is how barometers like the one on the wall work. Now, a storm is an atmospheric disturbance that can develop when a single air mass, within a single air mass, or may develop along the boundary between air masses, the frontal boundary. And storms can be divided into two categories: local storms and tropical storms. Now, local storms are what you regularly experience. Things like rainstorms, thunderstorms, ice storms, snowstorms, and tornadoes. They're regular old storms that happen around. Tropical storms are the massive storms that can form over the ocean, fed by warm water evaporating, that are things like hurricanes and cyclones and whatever the heck Superstorm Sandy was back in the day. I just remember that because, you know, it killed my power. So local storms. Let's start with local storms. A rainstorm is a heavy localized downpour, 1 to 3 inches per hour is when it's raining, and it's raining a lot. A thunderstorm is a rainstorm with lightning, thunder, and sometimes hail. So the kind of clouds that produce lightning and thunder tend to be big. Those are also the kind of conditions that can produce hail, because hail requires large clouds with big circulation in them. So the difference between a rainstorm and a thunderstorm is that a thunderstorm has lightning. That's it. So lightning is a discharge of electrical energy. It's just like a spark. So if you're ever in the winter walking around, you touch a doorknob, you get a spark, a static spark from your finger to the doorknob or something like that. The same thing, just with lightning, it's on a much, much bigger scale. It's just a discharge of electrical energy. So what happens is, much like static electricity builds up, you get a separation of charges within clouds. So what happens is the tops of clouds and the bottoms of clouds get a separation of charges, and this creates the bottom of the cloud gets charged, the ground reacts to that, and you can have a discharge within the cloud from the top to the bottom, or from the bottom to the top, or you can have a discharge from the bottom of the cloud down to the ground. So lightning occurs when there's a separation of charges due to the breakup and movement of water droplets. We don't fully understand the process that leads to this separation of charges. We know it happens. But fully understanding why like friction can separate charges is not, that's something that is not fully understood yet. It's still being studied. But as the charges separate, an electric potential arises between the top of the cloud and the bottom of the cloud, but also between the bottom of the cloud and the ground. And lightning can occur in several ways. You've got this buildup of charge. And charge doesn't like being near similar charges. So it wants to go somewhere else. So you can have lightning entirely within a cloud. This is intra-cloud lightning. That's like from the bottom of the cloud to the top of the cloud. Between two clouds, you can have cloud-to-cloud lightning, lightning going from one cloud to another. You can have lightning that goes from a cloud to the ground. This is cloud-to-ground lightning. This is the most dangerous to humans and property because this is the one that actually makes it to the ground. And you can also have air discharges where lightning just discharges into the open air. So the most dangerous form of lightning is, of course, the lightning that makes it to the ground, because in general, we are not heavily affected by lightning happening up in the sky, in the clouds, between the clouds, things like that. It affects airplanes and stuff, but in general, it's not something you have to worry about. But if it hits the ground, well, there's a whole bunch of electricity traveling through lightning. It gets super, super hot, and so it's very destructive. So on average, about 200 people a year are killed by lightning. Because if you get hit by lightning, you have an enormous amount of electrical energy running through you, which superheats your flesh, and that's not a nice thing to have happen. And it can also disrupt systems throughout your body, like your nervous system runs on electrical charges, so it can stop your heart or disrupt your heart processes, things like that. Now, thunder is the compression wave formed by lightning's sudden release of electrical energy. So basically, what happens is that lightning passing through the air superheats the air. It gets really, really hot. And that makes the air basically explode outwards. And that's what you hear as thunder. And if the lightning is very close, 100 meters or so or less, you'll hear a single loud clap. If the lightning's at a distance of 1 kilometer or more, the thunder consists more of a rumbling sound. And you can't hear lightning more than about 25 kilometers away. Can't hear thunder more than about 25 kilometers away from the lightning. And you could use how long it takes to hear thunder from when you see the flash of lightning to figure out how far away the lightning is. Because the light travels so fast that it's essentially instant. So you can basically use the speed of sound to figure out how far away the lightning is. So here's a short video clip about lightning and the science thereof.
The image is unmistakable. Lightning is one of the most incredible natural phenomenons, and one that scientists are still learning about. It's a common occurrence during summer when the heat of the day is broken by strokes of lightning. Worldwide, it's estimated lightning occurs 50 to 100 times a second. The greatest concentrations of lightning strikes are in Central Africa, the Himalayas, and South America. Lightning is often seen flashing between storm clouds in the earth. The bursts of light are pure electricity. Scientists don't fully agree on what actually causes the electrical charge to be dispersed, but it is generally thought that lightning often occurs within the downdrafts and updrafts of thunderstorms. Lighter particles moving toward the top of clouds become positively charged, while heavier particles heading toward the bottom become negatively charged. When the positive and negative charges grow large enough, lightning is released between these regions. Most of the lightning takes place within the cloud, but some strikes the earth in bold flashes. In these cases, the charge escapes the cloud, making a branching path that reaches for the ground. The energy of the lightning strike contains hundreds of millions of volts and lasts only a fraction of a second. What seems to be a single flash is actually a series of return strokes of electrical energy reaching back up into the clouds. The path reaches temperatures of around 50,000 degrees Fahrenheit. This extreme heat creates the booming thunderclap as excessive pressure within the lightning path expands at supersonic rates on return strokes. In the U.S., lightning occurs most often in Florida. Its hot, moist climate is perfect for creating thunderclouds, which produce lightning. But lightning is a deadly natural phenomenon, taking nearly 100 lives a year on average in the U.S., more than hurricanes or tornadoes. During electrical storms, experts warn that people should seek shelter inside a building or hard-topped automobiles, and if caught in the open, avoid high ground and isolated trees. Lightning is a powerful force of nature and one to be cautious of.
So yes, if you're stuck out in the open, getting inside of a hardtop car is probably your best move, because the hardtop car, it's got metal on the outside. The lightning, if it hits the car, will just flow around the outside and into the ground, and it won't affect you inside it. You'll be protected in what is basically a Faraday cage. So, you know, people who work around potent electrical things will wear like chainmail suits, or this is actually worn by people who work with like power lines, or you can work for when you're doing like demonstrations where you're generating giant bolts of lightning. You can use like a Faraday cage, which is just like a metal cage, and the electrical current will go around the outside. So with lightning and thunder, you can figure out how far away the lightning is. A lightning flash will travel at a speed of 300,000 kilometers per second. That's the speed of light. And that is so fast that it's effectively instant. You know, it's 300 million meters per second. It's super, super fast. While the sound only travels at about a third of a kilometer per second or a fifth of a mile per second. So the difference in speed is literally like a factor of a million. 300,000 kilometers per second to a third of a kilometer per second. It's about a factor of a million. So because the light is a million times faster, you don't really need to worry about how fast it's going. Thunder is sound. It only travels at about a third of a kilometer per second or a fifth of a mile per second. And therefore, the lightning flash is essentially seen instantly, but there's a delay hearing the sound of the thunder. I'm certain you've experienced this. And if you measure the time between the flash of lightning and the sound of thunder, you can figure out how far away it is. So if you see a flash of light and it takes 5 seconds to reach, and it takes 5 seconds for later, you hear the sound of thunder, then that lightning is a mile away or 1 2/3 kilometer away, about 1.6 kilometers away. So that's basically it. For every 3 seconds, it's a kilometer away. For every 5 seconds, it's a mile away. So here's an example. Suppose you notice an approaching thunderstorm, you see lightning, and then the thunder is heard 5 seconds later. About how far away is the storm in kilometers and miles? So given that the time is 5 seconds, velocity is 1/3 of a kilometer per second, or 1.5, 1/5 of a mile per second. 1/3 of a kilometer per second times 5 seconds is about 1.6 kilometers. 1/5 of a mile per second, or 5 seconds, is 1 mile. So if you're hearing the sound of thunder 5 seconds after you see the flash of lightning, the lightning's a mile away. Some other local storms you can have. Ice storm is one that occurs when the surface of the earth is below freezing when it's raining, and so the rain freezes on contact with the ground, and it builds up a layer of ice, and this is awful. And the weight of ice on trees and power lines can cause significant damage. And also, it coats everything with ice, which is miserable and dangerous because surfaces get really slippery and things like that. And a snowstorm is any storm with an appreciable accumulation of snow. And when a snowstorm additionally has high winds and low temperatures, it's called a blizzard. So when a snowstorm is more severe, has high winds, low temperatures, then it's a blizzard. That's the difference. Blizzard is just an extreme snowstorm that has high winds, low temperatures. Now, the most violent of storms is a tornado. Tornadoes form when warm, humid air collides with cold, dry air. The best place in the world to form tornadoes is the middle of the US, Tornado Alley. And we are on the northern edge of Tornado Alley. So tornadoes may not be as large as other storms. Their concentrated energy results in big destructive, not even the northern edge, we're just in the northern part of Tornado Alley. It extends past us. Great destructive potential. The problem with tornadoes is that they occur over such a short period of time with such complicated conditions. We can tell if conditions are possible to form tornadoes, but it's hard to tell if a tornado is likely to exactly form. We don't fully understand the process tornadoes form in, and they happen for such a short period of time, they're very hard to predict. So tornadoes may not be as large as other storms because they're so concentrated, they have extreme destructive potential. They're most common in the US and Australia, and most tornadoes in the US happen between the Rockies and the Appalachians, and we're heading into peak tornado season. April, May, and June are peak tornado season. Because that's when the conditions are right to create the kind of storms that can generate tornadoes. And the notifications for tornadoes, you get tornado watches when the atmospheric conditions indicate tornadoes may form, and tornado warnings are when an actual tornado has been sighted or indicated on radar. And the best thing to do, get inside, get away from windows, because the most dangerous thing is windows shattering and covering you in glass, with broken glass. Yeah. Try and be in, we'd actually be pretty safe in this room. We're far away from windows, we're inside solid building. We are unfortunately at the top of a building, but it's a pretty solidly constructed building. Would be better if we were down a floor or two. Yeah. So here is a short video about how tornadoes form and our understanding thereof. We don't fully understand all the details of tornadoes, so but we have a general idea of the process.
The average tornado has a lifespan of just a few minutes, but that's more than enough time for one of the world's most destructive weather events to form.
It's so short, it's so hard to predict.
The most extreme tornadoes can last for hours, span miles in diameter, and whip up wind speeds over 300 miles per hour. To prepare for these dangerous weather events, meteorologists have spent decades researching how tornadoes come to be. Tornadoes develop out of what's called a supercell thunderstorm, which is a normal thunderstorm with a persistent rotating updraft at its core. This rotating updraft grows into something called a vortex, a spinning column of air at the center of the storm. As a supercell grows in size, the vortex in the middle will begin to tilt, pulling warm air and moisture upward and pushing cold, dry air down toward the ground. The updraft of warm air causes the vortex to swell with water vapor, creating a spiraling funnel cloud. The cool downdraft begins to battle the funnel cloud's upward spiral, focusing the cloud into a smaller area and increasing its speed. With enough pressure and weight from the battling hot and cool air, the funnel cloud is forced down to the ground and a tornado is born. Modern technologies like Doppler radar allow meteorologists to track the moisture and pressure in the air, allowing them to notice the early stages of a tornado forming before the funnel cloud is even visible. And with every second of early warning, more damage can be prevented and more lives saved.
So, the tornado scale is the Fujita tornado scale. This was developed in 1971 by T.T. Fujita of the University of Chicago, just a few miles up the road. And so this is the enhanced Fujita tornado scale, and it's based on the wind speed. So the EF0 is wind speeds of 65 to 85 miles per hour. You get some damage to roofs and chimneys, branches broken off trees, shallow rooted trees pushed over, signboards damage, moderate damage. EF1 is 86 to 110 miles per hour. You get roofs severely stripped, mobile homes overturned or badly damaged, windows and other glass are broken. This is considerable damage. EF2 is 111 to 135 miles an hour. Roofs are torn off of frame houses. Mobile homes are demolished. Large trees are snapped or uprooted. Light objects are turned into missiles, and cars are lifted off the ground. This is severe damage. EF3 is 136 to 165 miles per hour. Entire stories of well-constructed houses get destroyed. Trains get overturned. Trees get debarked. Heavy cars are lifted off the ground and thrown. This is devastating. Damage. EF4 is 166 to 200 miles per hour. Well-constructed houses and whole frame houses get completely leveled. Cars are thrown and small missiles are generated. This is total destruction. And EF5, strong frame houses are lifted off foundations and swept away. Automobile-sized missiles fly through the air in excess of 100 feet, 100 meters or 300 feet. And steel reinforced concrete structures get badly damaged. This is an incredible phenomenon, but these are the most rare, most crazy and powerful tornadoes in existence. And here's the average number of tornadoes per year. And as you can see, we are not in, we're in the 5 tornadoes per 100,000 square miles area. Well, I guess 3 to 5, because it goes down right at the edge of Lake Michigan. But you can see we're still in Tornado Alley. And so this is, average number of tornadoes per year. They happen. They happen up into Michigan and such. I remember I was working when I was younger, I was working at a camp up in lower Michigan, and they had a tornado had hit and just cleared out a big chunk of forest. There was this big clearing that was where a tornado hit. So the next thing we'll talk about is tropical storms. So tropical storms are things like hurricanes. So these are massive weather disturbances that form over oceanic regions. But that is all for today. We will have a lab today at 10:15. So make sure to come back for the lab. So there is a lab today. Make sure to be here for the lab. And you can turn in your time in the sun lab because that is due today. So I'll stop sharing and I'll see you all back at 10:15. So for those are here remotely, make sure to come for the left.